Thank you very much. So, today I'm going to talk a little bit about why real-time systems aren't trivial, and to emphasize the point, we're starting with roughly a 5-minute delay. So let's get going. You've heard this is the official CV. The interesting one is I'm very much a tech guy. I taught myself assembly programming on my father's Commodore 64 in the late 1980s. And I've been involved in benchmarking microcontroller implementations of the secure hash algorithm 3 candidates back in the NIST competition from 2009 to 2012. So I have a little bit of a security background. And lastly, I've been involved in microgravity plant experiments. That was fun. But today we're going to talk about SDV and real-time. It's going to be a short inspirational talk like the others, 20 minutes, 25. So things will move fast. Feel free to drop me an email later. I can send you the slide set so you can look stuff up. Take this as a directory of what might be interesting for you to look at later. Okay, let's get started with the evil of complexity. Why is complexity bad in the year 1986? Well, let's see. Does anyone remember this? Or maybe this? And look, there's icicles. And that is called blow-by, and that's what happens when you have a rubber gasket that isn't really tight anymore after being exposed to low temperatures. Well, and then this blows against that tank, and the tank is full of hydrogen. So while we're in the US, some of you might think of Lakehurst, others might think of Hindenburg, and that's exactly what happened. The hydrogen blows up. Space Shuttle Challenger, 1986. Complexity that went wrong. Well, let's talk about German issues with complexity. Behold, the Intercity Express, the pride and joy of German rail. The year is 1998, when the Intercity Express 884, Wilhelm Conrad Röntgen, is on a trip to the north of Germany. And guess what? A rubber dampening part causes part of a wheel assembly to break, which flips a switch under the train while it's passing in front of a bridge. Half of the train goes to the right, the other half straight ahead, and they hit the bridge. Over 100 people. That stopped high-speed trains on the entire world for about 2 hours. TGV, Shinkansen, all shut down while everybody in the world tried to figure out what in the world happened here. What happened? Too much complexity. So, those of you familiar with telecommunications might know the OSI model. Here's the extended one. Layer 8 is the financial layer, layer 9 is politics, and then on top there's religion. Oh, but to be fair, if you look at the article by religion, the guy related to developer religion, like, oh, only this broken language, only this paradigm is the right thing. Anyway, the bitterness of poor quality remains long after the sweetness of a low price is forgotten. If that sounds familiar, it's because Ben Franklin. These constraints, when applied to already complex systems, stuff happens, bad stuff happens. So, why is complexity bad today? We're not here for a history lesson. Well, us human beings can handle about 5 to 7 things in our conscious mind, no more. So anything that's too complex, we can't comprehend it, which means we need to make things simpler. And how does this relate to software? Well, here's a quote I like. There are no complex systems that are secure. Complexity is the worst enemy of security, and it almost always comes in the form of features or options. Software updates, downloadable features. And complexity is a measure of how many things interact at any one point. They need to touch each other, otherwise it's not complexity. Got that from a book. that was extremely helpful in my master's work. How do we handle complexity? How do we not handle complexity? First of all, remember the KISS principle. The world needs more kissing. If you can do something simple, do it simple. Do not add unnecessary complexity. Nobody needs that. Then, if you find the time, take a look at the work of Daniel Kahneman. Thinking fast and slow. System 1 is the fast one, where we work autonomously. It's low effort, and it works great until it doesn't. See the space shuttle and the high-speed train. System 2 is slow, it's high effort, it's costly, and that's what gets the job done right for a price. Your teams will need to take their time. And of course, break problems down into smaller parts, divide and conquer, unit testing, that kind of stuff. Important, clear and simple interfaces. All right, so much for complexity. Now, you were promised something about memory, so let's talk about throughput and latency. You can have your cake, or you can eat it. Some promise that you can have both, but it's usually not the case. Faster takes longer. Sounds weird, but there are certain rules of physics we cannot circumvent. Propagation of electrical signals in silicon are not infinitely fast. So any logic we build, if you want to clock it to high clock rates, you need to slice it up and pipeline it. And that's great, it gives us high clock rates. But now, in order to finish a single unit of work, we need many steps. And those of you who were around for the introduction of the Intel Pentium 4 will remember the thing performed worse than the Pentium 3 in many scenarios, even though it was clocked much higher and was more modern. Why? Long pipeline. Why is long pipeline important for SDV? Because you're running on application processors, that's the A in ARM, and they have high clock rates, but also a high latency expressed in clocks, and low predictability because of that. Real-time cores are better, Cortex-R, you heard people talk about the application processors and then the Cortex-Rs, that's the background here, and M are the really small microcontroller cores. They have low latency, are very predictable, but you cannot clock them to the gigahertz range. So, how did these execution times develop? 8051, stone old Intel microcontroller. Now everybody's awake, excellent. Basically, any code you ran always took the same time. There was no variation. Best case execution, worst case, average case, all the same. Then with some PowerPC 5000 series, everything got faster, but the worst case now is quite different from the average case. And then with the Cortex A76, you see how the worst case sticks out. So designing for the worst case is no longer feasible, and you get higher clock rates, but you get long pipelines, caches, and that gets you this. Average core execution time goes down, worst case goes up. So the question becomes, okay, we have these powerful processors, or maybe we will have them in the future. We heard about it this morning. You do the software now to deploy on a hardware that will exist in 3 or 4 years. Okay? So here's the powerful next project hardware. It's got everything. Multi-gigahertz, multi-core, single instruction, multiple data, digital signal processing, hardware crypto accelerators, gigabit Ethernet, all the bells and whistles. And then somebody takes a look at it and says, yeah, but we need some costs down. That external memory interface, that's a lot of pins. Let's halve that. And suddenly, what in the world happened to my nice project? Okay, that's a theoretical scenario with a nice meme. So how does it look in reality? Back in the early 1980s, the CPUs were below 10 megahertz. The RAM was so fast, the CPU never had to work. Then in the 90s, we got those chips that ran at twice the speed internally. Suddenly things mattered. In 2009, implementing AES on an Intel processor was, for the first time, faster if you computed stuff instead of looking it up. Because that's how far the memory subsystem had fallen behind. And now today, CPUs and GPUs just wait for the memory to catch up. So here's the CPUs, some benchmarks, there's the source. The takeaway is the top positions are those that come with huge caches on the chip, or in plain English, fast memory. That's what wins the game here. Graphics processing units, aka AI accelerators. Somebody introduces a new model and manages to get it slower than the previous model, even though the computation engine is much better, but they reduce the memory interface to the point where the thing just can't compete anymore. Now, what does this have to do with automotive? Let me tell you a story from one of my projects. Advanced driver assistance system development taking place in the office. 3 teams, 3 cores. Every team get their software, traffic sign recognition, lane keeping assist, and distance control to preceding cars. Okay, great. They develop their stuff, tests work, performance looks good, everybody is happy. Each team has their own eval board, they're all identical, they run their stuff on their own core and their own core only. Great. Then we integrate into the real ECU, and the car goes onto the parking lot. Wow, doesn't work out. Why? Complexity is a measure of how many things interact at one point. What's the one point here? The memory interface. For the first time, those 3 independent components running on 3 independent cores tried to run at the same time and access the RAM at the same time, and everything broke down. The thing couldn't even leave the parking lot. It switched off, done, finished, out. Memory bandwidth. Why? Too expensive, they have the interfaces. And that's a real project. So what do you do then? You promote data locality. You try to make things cache friendly, there's literature on that. You specify and monitor memory bandwidth requirements for software. So zero trust not only means the stuff's not supposed to read my secret keys, it can also mean the stuff has to be rate limited so it doesn't block my memory interface. And the best thing you can do is memory Tetris, that's what we call it. That customer here, they had very sharp math PhDs, and I didn't understand what they did with the algorithm. My colleagues didn't understand it. We didn't need to. We just made sure that the data they needed was placed into local buffers using DMA, so their algorithms could run. And guess what? The thing could leave the parking lot and went into series production. Memory access times. Always monitor timing changes when adding new software. So finally, how do we get to an SDV? Well, if we look at classic timing requirements from classic AutoSAR, it looks like this. And don't try to read everything. This is just there to tell you, yeah, it's well specified, and there's documentation on it, and so on, but that's not what we need in software-defined vehicles. In software-defined vehicles, we move from tasks and interrupt service routines to event chains, or you would call them applications. And it looks like this. Let's say you have your advanced driver assistance system that can recognize when something's on the road. And you don't just want to recognize it and turn on the red light before it goes boom. You want to do something. Ideally, you steer the car around, but electric power steering is a real-time thing, so you have an ECU for it. Okay, great. So what are the steps? Well, find the object, see which way you can go, and then talk to the electric power steering to move around the obstacle. Now that's a nice application. How does it look? A bunch of components, and they all need to work, and they need to work in real time. So we got the detection of the foreign object. We have the trajectory plan. Do we go left or right, and how far do we go? We have the required steering angles. Then that gets passed on to the electric power steering that performs some math on what to do with the electric motor. And then finally, the motor control issues PWM values that go to power MOSFETs that drive stuff. And there we are. That's everything that's necessary, and it needs to be done in a certain amount of time, because if the steering hasn't moved for too long, you've already hit the arc. So that stuff needs to be tracked. And this is how it can look. If you are able to put your POSIX or application course and your real-time course or a ECU that handles that onto one timeline and track the entire chain of events, and then you get your total end-to-end time, and if that's within spec, great. And if it's not within spec, you have the individual steps to find out where did it go wrong, which component took too long, under which conditions. So, best practices for distributed software components: break the operation into steps. Steps you can measure, steps you can verify. We call them event chains. Specify them, ideally when to do the requirement specifications. Include end-to-end timing requirement. Check that your system architecture and software architecture are able to support this. Decompose the chains into the individual steps. Then verify them. And supervise those critical chains in the final product. Start early, automate. If the test needs to be performed by a person, that person will be on vacation, that person will be occupied by some task force or war room or crunch time, whatever you call it, that person will be unavailable, the test will not be done. So what often happens is people set up a bunch of functional tests, and once everything works functionally, someone says, have we looked at the timing? Oh, let's add a timing test. Not a good idea. Add your timing tests as soon as possible, because you need to run the functional tests anyway. And while you're running them, obtain the timing numbers on the side that allows you to track them while your software develops. And that's the better approach. Start early. Or some people would say shift left. Capture the CPU load, capture your execution times, jitter, all of that stuff on the fly while you're performing the functional tests anyway. You're paying for that test time, make it pay you back. So to sum up, some do's and don'ts. Do not let timing just happen. Be aware of it. Don't let task forces or war rooms control your timing methodology. Don't burn out your best experts in timing debugging. 3 missed long weekends with the family. Eventually, they will ask for offers in other places, and you don't want to lose these people. And of course, if you fail to plan, you obviously have to fail. And the do's would be consider timing in all development steps, from the requirements to the final verification. Every project must or should have a timing expert assigned. So there's one person people can go to when they say, looks funny, just like you have your safety guy. Not everybody's an A and B expert, but everybody knows where to go if something smells funny. Introduce the same thing for timing. Establish automated tests that run alongside your already existing functional tests, and get the timing infrastructure in the platform if you have a platform. And with the software standardization people have been talking about this morning, makes a lot of sense to think about it in that standard platform you're going to do. And obviously those are the important parts. So what can we do with tools and techniques? Well, here's the big overview of tools, and some of them are independent of scheduling, others are dependent on scheduling. When we're talking SDV, we're basically talking about the stuff that's dependent on scheduling. You can trace and measure. This morning you heard talks about the information of tracing, and yeah, absolutely, you need to know what's going on. Also, scheduling simulation can be useful, especially if you know there will be this new software component, this new application, but it's not here yet. You somehow want to get in front of the stuff again, shift left. And static scheduling analysis can be very useful. Can we prove that it actually can work? And all of that, if possible, on distributed, synchronized, full event chains, because you need to see the full chain that's going on and not just isolated software. Just a few weeks ago, we hunted a bug in a software component that was supposed to take some navigation data from a satellite antenna and broadcast it on the vehicle bus every 100 milliseconds. The thing didn't work right. OEM was pretty annoyed. The ask was, well, it turned out their scheduler, after waking up, didn't call the component every 100 milliseconds where it's supposed to emit the messages. It just called it 3 times in 7 milliseconds and then didn't for half a second and then started to do funny stuff. That software developer could debug his code from here to eternity. The problem was never. So you need to consider the full chain. And yes, there's tools for it and we sell them. And yes, there's customers for it. Okay, so much for the marketing talk, that's it. Wisdom of the not quite so ancients. If you want to snap a photo of a slide, then I highly recommend you do that. Or you send me an email afterward. Every one of these books saved my bacon at some time. They're really, really helpful. That thing helped us at Bosch to specify new CPU architectures together with a huge semiconductor manufacturer. My colleague basically learned it by heart. It was the third edition back then. It helped a lot. That's the Canavan I mentioned. That's cryptography engineering. The book is now pretty old, but the principles are still very, very, very current. And always think about your teams. Tom DeMarco is a very good source for that. And yeah, if you want to know stuff about embedded software timing, there's a book by my boss Peter, and you can get it from Springer. And if you work for a large company, you probably have Springer access anyway. So your developers can just go there and basically download the PDF for free because it's all prepaid. Otherwise, contact us, and there's a limited number of books we can just send out. And that's it. Thank you very much. Any questions?